In this exercise, I'm going to be showing you how to calculate the area between a circle and a parabola using double integrals and polar coordinates. I'll demonstrate how to define the region in terms of integrals, and if you stick around until the end, I'll show you how to evaluate the integrals. We have a circle with a parabola passing through it, creating an area of intersection shown here in red on the diagram. We are tasked with finding the area of intersection shown in red using double integrals and polar coordinates. The equations of the circle and the parabola are shown in Cartesian coordinates. The circle has a radius of the square root of 2 and is centered at the origin. Its equation is x² plus y² is equal to 2. The parabola has an equation of y equals x². The first step in finding the area is to convert the equations of the circle and parabola from Cartesian to polar coordinates. To do this, we'll substitute rcosθ for x and rsinθ for y. So beginning with the circle, in Cartesian form we have x² plus y² is equal to 2. And making the substitution for x and y, we get r² into the bracket of cos² plus sin² equals 2. And using the trig identity where cos² plus sin² is equal to 1, we're left with r² equals 2. And taking the positive square root of both sides of the equation gives r equals the square root of 2. And for the parabola, in Cartesian form we have y equals x². And making the substitution for x and y, we have rsinθ is equal to r² cos²θ. And dividing both sides of the equation by r, we have sinθ is equal to r cos²θ. And therefore r is equal to sinθ divided by cos²θ. Now that we've found the radial distance r for the circle and the parabola, let's look at the behavior of r as we use it to compute the region shown in red. As r rotates in a counterclockwise direction between, at this stage, unknown angles of theta, where theta is the angle r makes with the x-axis, the radial distance covering the area shown in red is determined by the parabola. This continues until the parabola intersects with the circle for the first time at some unknown angle of theta, at which point the area is determined by the circle. And when the parabola and circle intersect for the second time, the parabola once again determines the area. In this exercise, the area shown in red is symmetrical about the y-axis. We can use this fact and calculate the area between theta equals 0 and theta equals pi by 2 radians and double the result to get the total area. To find the angle of theta between 0 and pi by 2 radians, where the circle intersects with the parabola, we can equate the polar equations. So we have r equals the square root of 2 and r equals sinθ divided by cos²θ. If we equate the two, we have sinθ divided by cos² is equal to the square root of 2. And if we replace cos² with a trig identity, 1 minus sin², we get sinθ is equal to the square root of 2 into the bracket of 1 minus sin². And expanding this out, we get the square root of 2 sin² plus sinθ minus the square root of 2 equals 0. For simplicity, if we now let x equal sinθ, we can solve this as a quadratic equation. So we have the square root of 2 multiplied by x² plus x minus root 2 equals 0. To solve this, we can use the quadratic formula. So using the formula to solve the quadratic, we get values of x equals 1 divided by the square root of 2 and x equals minus the square root of 2, where x is equal to sinθ and sine theta is in the range -1 to 1. So we can eliminate minus root 2 as it's less than -1. So theta is equal to sine to the -1 of 1 over root 2. And we know that the circle intersects with the parabola somewhere between 0 and pi by 2. Therefore, in this instance, theta must equal pi by 4 radians. Now we understand the region. As the radial distance r rotates about theta, we can define the limits of integration of the outer integrals. As r rotated about theta, we saw that it began at theta equals 0 and continued to where the parabola intersected with the circle, so at theta equals pi by 4 radians. It then continued from theta equals pi by 4 radians to theta equals pi by 2 radians, and due to symmetry we saw that this would give us half the area. So to get the total area, we need to multiply both double integrals by a value of 2. Now let's look at what happens when we sum infinitesimally small pieces of area along the radial distance or in the r direction. This will help us define the inner integrals. When we integrate in the r direction, this will represent the inner of the two integrals. This diagram represents a sector of the region capital R. The angle it makes is infinitesimally small and is denoted by d theta. Within the sector, we have infinitesimally small pieces of area denoted by dA. The size of each area is the length multiplied by the width. So in this case, dr is the length and r d theta the width. So dA is equal to r dr d theta. To find the total area of the sector, we integrate or sum in the r direction. When we sum or integrate along the radial distance r, we begin at the origin, so where r equals 0, and continue until the parabola intersects with the circle, so where r equals sine theta divided by cos squared theta. Then we continue from the origin, so where r is equal to 0, until we reach the perimeter of the circle, so where r is equal to the square root of 2. So now we can add the limits of integration when we integrate or sum along the radial distance r. We saw that for both the inner integrals, we began at the origin, so where r equals 0. And for the first of the inner integrals, we travelled from the origin to the parabola, so where r is equal to sine theta divided by cos squared theta. And for the second of the inner integrals, we started at the origin and continued until we met the circle, so where r was equal to the square root of 2. And in each of the double integrals, we are summing infinitesimally small pieces of area, dA, which translates to r dr d theta. So now we've defined our double integrals, we can begin the evaluation process. And beginning with the first of the inner integrals, we want to integrate between r equals 0 and r equals sine theta divided by cos squared theta r dr. Using the power rule, its antiderivative is r squared divided by 2. And plugging in the integration limits, it evaluates to sine squared theta divided by 2 multiplied by cos to the power of 4 theta. And for the second of the inner integrals, we want to integrate between r equals 0 and r equals the square root of 2 r dr. And using the power rule, its antiderivative is r squared divided by 2. And plugging in the limits of integration, this evaluates to 1. And now moving on to the first of the outer integrals, we need to integrate between theta equals 0 and theta equals pi by 4 sine squared theta divided by 2 cos to the power of 4 theta d theta. And then we need to multiply this result by 2. And its antiderivative when multiplied by 2 is tan cubed theta divided by 3. And plugging in the values for theta, this evaluates to 1/3. And for the second of the outer integrals, we want to integrate between theta equals pi by 4 and theta equals pi by 2, 1 d theta. and we need to multiply this result by 2. And using the power rule, the antiderivative is theta, and when multiplied by 2 gives 2 theta. And plugging in the values for theta, we have pi minus pi by 2, which evaluates to pi by 2. And so the area of our region capital R evaluates to pi by 2 plus 1/3.